Well, we spend the first part of this unit talking about work, how you calculate it. There's all kinds of little details that go into that, things related to dot products. And maybe the newest thing for you is how you have to use integral calculus or integration to calculate work if you have a force that's not constant. But I think in all of that, maybe you've missed what the big idea of work is. Like, why do we need to know something about work? And it's because it's so closely related to energy. In fact, one of the best examples that I've heard about the connection between the two is that work is kind of like the currency that you use to get energy or to get rid of energy. So it's like if you want some energy, it's going to cost you some work. So let me show you actually a very simple example of this. And this will look a lot like something that we used back when we were doing Newton's laws. So we've got a 10-kilogram object that's just sitting on the floor. What we have to imagine now is we're dragging it across the floor using some kind of applied force here, 50 newtons applied up maybe with a rope. And we've got a rough floor, so there's some friction opposing it. And the question might be, how much energy does this box gain if it slides over 5 meters? That's one of the things you'll notice about work energy problems. There's almost always going to be a distance involved. Whereas when we used Newton's laws and we were talking about accelerations, usually there was time. So work and energy don't have a good connection with time, although you could force it to be related to time. It's almost always connected to some kind of displacement. And that's because of the way the work is calculated. So what we do is we just look at all the different forces acting on the object, and one at a time we figure out how much work is that force responsible for. So I think the most obvious one to start with here is this applied force. So we'll call that the work done by the applied force. And the definition of work is it's a dot product of the force and the displacement, which we'll call delta x. I'm going to put little vector symbols over these because a very formal definition of a dot product means we're multiplying two vectors together in this way. So this in particular is the applied force. So here we've got 50 newtons, and we've got a displacement of 5 meters. I'll use 5.0 here. But remember, with a dot product, we have to account for the direction between them. If they're perfectly parallel, lined up with each other, then we're fine. But if there's any angle in between the applied force and the direction of the motion, we have to account for that parallelness with the cosine of that angle. So in this case, the cosine of 37. So when we multiply all that out, we will get 200 joules of energy. And you can check me on that. 200 joules of energy. So what other forces do we have here that are causing some work to be done? Well, let me show you a couple that are not causing work to be done. We of course have a gravity force that would be pointed downwards, but because gravity has absolutely no parallelness with the horizontal motion, then it can do no work at all. The angle in between them is 90 degrees. So if you imagine putting cosine of 90 in, you're going to get a big zero. The same is true for the normal force here. Back in the Newton's law chapter, we would have calculated the normal force. But it doesn't matter to us here because it can't do any work if it is perpendicular to the motion. So the only other force here that we have that can do any work is this leftward friction force. So let's calculate the work done by the friction. And that again is the product of the friction force. This is a kinetic friction dotted with the displacement. So the amount of friction here is 20 newtons. And we have a displacement still of 5 meters. Oops, I said 5.0. Let me squeeze that in there. And then the cosine of the angle in between those two directions. Well, the displacement is rightward, but the friction force is leftward. So we put in a cosine of 180. Now that's equivalent to -1. All that does is it makes this whole value negative. -100 in this case. Sometimes a lot of people just kind of use the shortcut. They know that the two vectors are anti-parallel with each other. That means opposite in direction. that it's always going to end up just a negative of whatever the product is for those two. So that accounts for all the energy. So the total energy is just equal to all the work done, which is 200 minus 100 for a total of 100 joules. And then we might ask a question like, well, okay, if we've gained 100 joules of energy as this thing moves 5 meters, then how fast is it moving? After 5 meters. Now, we would need to know something about how fast it started. Let's just imagine it had no motion to begin with. So then we're going to use the connection that work is what causes the change in the kinetic energy. Remember, work is like the currency. It's how you buy energy. So we're just going to buy ourselves 100 joules of energy. And if we started with none, then that will just equal 1/2 mv squared. That's the very definition of kinetic energy. So 100 joules of energy is 1/2 times our 10 kilograms times v squared. And I'll do a little math with my calculator here. We're going to take the square root of 20 at the end and get about 4.5 for the velocity. 4.5 meters per second. And again, see that last little bit there? That was after a certain amount of distance covered. Whereas when we did Newton's laws, usually we would say after so many seconds of acceleration, we'd build up to a velocity. Again, only because we're not really relating anything here with time. Everything with work and energy is kind of tied into displacements. Just something to get used to. So that's really how you connect work and energy. And this can take so many different forms, from maybe we have a spring doing some of the work. Maybe we've got gravity doing some work. If things move up and down, we can have gravity get us work. Or maybe take work away if we're moving up and gravity's down. So you do have to just account for the directionality of everything when you do the dot product, and the work energy theorem will take it from there. So hopefully this gives you a good nudge for any kind of problems that you run into. And if you need any more help than that, you know where to find me. Thanks for watching.